Hello guys, this is our first video in gas power cycles, and the objectives of this chapter are to evaluate the performance of gas power cycles differently from the Rankine cycle, in which we have change of phase. In these cycles the fluid will remain as gas or as vapor throughout the whole cycle. We're gonna develop some simplified assumptions to review the cycles and review of the operation of reciprocating cycles like auto and diesel. Both closed such as auto and diesel, and open such as Brighton gas power cycle. We already mentioned this. And some insight of jet propulsion cycles, since G is now a big employer here in Creta. I think this is just useful for you. And we're going to skip the cycle analysis until we saw that chapter. Okay, so some basic considerations of the gas power cycles. We can recognize that most power producing device operating cycles, you just think of your car or your motorcycle and or truck, and you can recognize that this move with cycles, but it could be also a power plant, the kind that you just can see in any concert. They have diesel power plants. Now, what is that ideal cycle? We can think of this. We can try to model a very complex cycle, which is difficult to do because of two things. One is dynamics. They are so fast that there's no time that they can reach equilibrium, and the second one is large irreversibilities. They go back and forth so quick that they have large irreversibilities. Remember that one of the sources of irreversibilities is sudden expansion or sudden compression. So what we are going to do is we are going to look carefully at the cycle and then try to think of processes that resemble the actual cycle. We are going to make some approximation that can make it closer to that. We already talked about Carnot. It's a reversible cycle and will have the highest thermal efficiency. They are not realistic for models. You can see here that just these parts are not in the ideal cycle. I mean, if this dotted line is a real cycle and the black line is the ideal, you can see that they don't match perfectly. But what we can say, or the assumption that we will make in this case, for instance, is that this can be modeled as a constant volume process, same like this one, with some error. This compression we're going to model maybe as isentropic or maybe as a polytropic process, and the price that we are paying is that we introduce this error. These models are powerful tools. They give us great insight of what we can get from the cycle and what we lose, because remember we have said that there's not such a thing as free lunch. Is that we lose some accuracy, right? Let me change the color of this. And because we are losing some accuracy, we should just take care of the conclusion that you get. You know that this analysis that we are getting is just a first cut analysis on gas power cycles. There are complete courses, complete books devoted to this. Just for our recall, we're modeling all these machines to be a thermal machine. We have high temperature reservoir, we have machine, and we have a low temperature reservoir. We get heat from this high temperature. This machine will produce some network, and due to second law we need to reject some heat to the low temperature reservoir. Okay, this work net, that's the total output. You can recognize that we are compressing here, so we are giving work to the machine, and then we are expanding here, so we are extracting work from the machine. The net will be what we have inside the cycle curve. So you can, just for you to remember, the network will be the difference between the workout and working. You want workout to be greater. Okay, so recall that we define efficiency as the network by the QN, and this could be in specific work or total work. And we can recognize from this first law diagram that can be also expressed as, so another definition of efficiency will be Q in and will give you exactly the same answer. Okay, let me just go back a little bit, and usually this dotted line which represents the actual cycle. Sometimes it's difficult to envision that this will be the actual cycle, so I'm showing here a diagram of a PV diagram of actual experiment. You can see this is measured, and reference is showing on the screen right now. See, you have two pressures and the pressure inside the cylinder. This was for a refrigerator compressor, but it's similar to what you will have on different performing different cycles. Okay. So, as we already mentioned, the ITESM diagram, what we have inside the curve is a network. We have two kinds of diagrams. We have the PV diagram and the TS diagram, the temperature entropy. While in both of the cycles, the area enclosed in the cycle is the representative work of the network of the cycle. They serve a different purpose, and PV diagrams are very useful to identify the work interactions, because we can remember that in our systems work is just because we have change of volume against some pressure. So PV is a perfect match for that. Now Q, TS, remember that Q it's function of delta T. So TS diagram helps us to identify the heat interactions. So we will use both diagrams in order to analyze these cycles. So before we go any further, we need to come with some assumptions for the cycles and the simplifications that we are doing. The first of them is that we are not gonna involve any friction. This is obviously not true, but this is one of the assumptions and simplifications that we are doing. We are not having any pressure drop, and we don't have any heating due to friction between the cylinder and piston, for instance, in the Otto cycle. We mentioned before that one of the complexities of cycle analyzing is that they involve the dynamics. They are very fast. So what we are going to assume is that along all these processes, we are going to have enough time to get equilibrium before we move to the next part. So we're going to talk about quasi-equilibrium error in each of the processes, the compression and the expansion. And sometimes, and that's true especially for the Brayton cycle, you have components that are connecting by pipes. So we are going to assume that those pipes, they have no friction at all. We already mentioned that, and we don't have any heat transfer. So they don't have any pressure, any temperature loss or gain. We just recall very briefly the Carnot cycle. You remember that it starts with an isothermal compression, then hold on. We have an isentropic compression, then we have isothermal heat addition, isentropic expansion, and isothermal heat rejection. Okay, that's easy to watch in the TDS diagram. Isentropic compression, isothermal heat addition, isentropic expansion, and isothermal heat rejection. This Carnot cycle gave us this efficiency, and will be the greatest efficiency of all the cycles that we can think. Just watch this TL and TH as this same TH and TL that we draw here. That are the reservoirs from where we are getting our heat. Okay, so this is the greatest that we can get in any two given temperatures. Okay, we are going to invoke another assumption that we are going to use through the gas power cycles analysis, and is what we call the air standard assumption. We can recognize that, let's say, in earth engine or in a diesel or in a gas power motor, that pretty much the mixture that we have in the combustion chamber is air and fuel, but it's pretty much air. You can recognize that when you have a lot of fuel, then you don't have enough oxygen to do the combustion, so you just have much more air than fuel in the combustion chamber. Once the combustion takes place, pretty much the combustion processes are still air. When we talk about combustion at the end of the semester, you will see that we call excess air. We need more air than the theoretical quantity needed to have a stoichiometric combustion. So we're gonna, because of this, we can change all this complex process, because the kinetics of this combustion is so complex that we are gonna change it by assuming that inlet and outlet is air, and that the energy released in this combustion is substituted by the heat addition. Okay. So this is one of the assumptions. The first assumption is that working fluid is air, and air behaves as an ideal gas. That's important. All the processes that make the cycle are internally reversible. We already discussed this. The combustion is replaced by the heat addition, and the exhaust process will be replaced by the heat rejection. Okay. Two more. So all these four are the air standard assumptions. If we invoke a fifth one, so I will put 5 here, is that when the properties of this air are considered room temperature, this will be 25 degrees, could be 27 sometimes because it's easier. These are 300 Kelvin, and you will see that these are the ones that are tabulated, so 25 and 27 for us will be the same. When we assume this, we will assume that we have cold air standard assumptions. So cold air standard assumptions that you have these four plus this fifth assumption. Okay, thank you. This is the end of the introduction. Couple of videos following the next one on solving gas cycles and pressurized entropy processes, and we're going to start with auto and diesel. Thanks.